This is part 2 of lecture 10, the transportation and assignment problems for IE 3340 operation research. In the previous video, we discussed the application of linear programming, specifically for the practical example of a transportation problem. And we mentioned that this problem is widely used in industry, specifically when you work for this shipment-oriented companies such as Amazon, UPS, FedEx, Walmart. They all deal with this type of problem in which you have to decide how to use your resources in ways in which you can ship your merchandise to the warehouses or to your stores, or to your clients, and so on. So in the previous video, we focused on what we call the balanced transportation problem. And a balanced transportation problem is a transportation problem in which you have the same amount of supplies that the demand that is required from your customers. So that's why it's called balanced. But that's not always the case. So in this video, we are going to discuss the difference between a balanced transportation problem and an unbalanced transportation problem. And also we are going to discuss how to address a problem that is unbalanced in terms of finding an optimal solution. So that being said, let's start with the lecture. So as I mentioned, a balanced transportation problem is when you have, or if the total supply equals to the total demand, then the problem is said to be a balanced transportation problem. So if you sum everything that you have available in your company or in your different branches of warehouses, and the total equals the total of all the store's demand, then you can say that that is a balanced transportation problem. So the summation of the supply, which is at the left side of this equation, is equal to the summation of all the demands, which is on the right-hand side of this equation. Balancing a transportation problem if total supply exceeds the total demand. So if a total supply exceeds the total demand, we can balance the problem by adding a dummy demand point. What that means is we are going to create this demand that is not real for the purpose of solving the problem. Since shipments to dummy demand point are not real, they are assigned a cost of 0. So the idea is that you are shipping to this dummy demand point, but the practical point of view is that those shipments are not actually happening. Remember, this is just a way to set up the problem so we can solve it. So if your demand, if the total supply exceeds the total demand, we create this dummy demand point that will allow you to send the additional supply to that demand dummy point, so you can solve the problem. On the other side, balancing the transportation problem is the total supply is less than the total demand. If the total supply that is strictly less than the total demand, the problem has no feasible solution. One or more of the demand will be left unmet. Generally, in such situations, a penalty cost is often associated with the unmet demand. The total penalty cost is desired to be minimum. So if you go to a practical application, let's say you work for Walmart, or you work for Amazon, and you are trying to set up a contract with a customer in which you're going to be supplying, I don't know, let's say paper towel to this demand or to this customer, and you are basically in a contract stipulating that you are going to supply 100 roll of paper towel every week. Typically, in such contracts, you will have a stipulation that will say that if you are not able to meet the requirements, then you're going to have a penalty. Penalty will say, okay, you will be charged, or you will get a discount as a customer of, I don't know, 10% if you're not able to supply all the amounts that were requested in the contract. So that's what we call a total penalty cost. So we typically have a penalty cost associated with unmet demand. So you want to minimize that cost. You want to make sure that you are able to supply, but if that's not the case, your customer will get some type of benefit. So in the MG model that we discussed in the previous video, suppose that the Detroit plant capacity is 1,300 cars instead of 1,500. The total supply equals 3,500, is less than the total demand, which is 3,700. Meaning that part of the demand at Denver and Miami will not be satisfied because you don't have enough. Your customer are requesting 200 additional units than the ones you have in your warehouses as or available to supply. So if the total supply equals the total demand, the problem is said to be a balanced transportation problem. Because the demand exceeds the supply, a dummy source plant with a capacity of 200 cars is added to balance the transportation model. The unit transportation cost from the dummy plant to the two destinations is 0 because the plant does not exist. The unit transportation cost from the dummy plant to the two destinations is 0 because the plant does not exist. Okay, so you are not actually, the model is not charging the system because it's not real, right? So that the idea is just to provide this modification to the model so we can actually solve the problem and get a solution. So before we get to this slide, let me show you the solution for this problem. So this is the balance model that we discussed in the previous video. This is the implementation in Excel. So here we have the data for the problem. So you are trying to minimize the transportation costs. These are the costs associated with moving items from Los Angeles to Denver and so on. So we have 3 suppliers and 2 demand points. We have capacities associated with each one of the supply nodes, and we have the demand associated with each one of the demand points. Okay, so we want to formulate this problem. And as we saw in the previous video. This is the formulation. So we have a decision variable associated with each link, like each supplier to each demand point, and there is a cost associated to it. So that's our objective function. We have a set of constraints associated with the capacity of the supply nodes, and we have a set of constraints that are associated with the demand points. Okay, so the problem is formulated in the same way. So we have six decision variables, 3 associated with Denver and 3 associated with Miami. And then we have the objective function, the constraints, the capacities are listed here, and the demand are listed in this second group of constraints. So if we solve this problem using the linear programming, the simplex method, we obtain this solution. So what this is saying is that the cost associated is this much, $313,000. And we are going to be sending 1,000 units from Los Angeles to Denver, 0 units from Los Angeles to Miami, and that makes sense. The cost is high. We are going to be sending 1,300 units from Detroit to Denver and 200 units from Detroit to Miami. And then no units from New Orleans to Denver, but 1,200 from New Orleans to Miami. Okay, so that's the optimal solution. And remember, this is the balance transportation problem for AMG. So now we have an unbalanced transportation problem. So what's stated here is now we have 200 less units in the supply than when compared to the demand. So we want to use a dummy plan, which is what's illustrated in this slide, to basically capture how many units are not going to be delivered because we don't have enough capacity. And this slide is showing you the actual solution. So what this is saying is that Miami is the city or the customer that is going to be short in terms of getting the units. So if I want to look at that I have the unbalanced version here. So as you can see now, when compared to the other model, the Detroit has 200 unit less in terms of capacity, right? So from 1,500, we went to 1,300. That was, we added this dummy. I'm making the capacity of the dummy node very big because it's not real, right? So I made it 10,000. And then we added the additional decision variables associated to the problem. And these constraints are also edited to add those additional decision variables associated with the demand. Okay, so if we solve this problem now, we get this solution. Okay, so essentially what you're seeing, even though there's no cost associated with the dummy, what you're seeing here is this. Miami is going to be short by 200 units, and that is what's going to happen. So for the unbalanced version of the problem, the way we deal with it is by adding a dummy supply node. And that dummy supply node is going to tell us how many units are going to be short and which customers are going to be not receiving the amount of units that they requested. So the solution shows that the dummy plant ships 200 cars to Miami, which means that Miami will be 200 cars short. The question I have now is, can you modify the model to make sure that a specific destination does not experience shortage? Okay, so that's the question. For example, if you want to make sure that Miami is not the city that is penalized, how can you modify the model to make sure Miami is receiving the units that are requested? So one thing that you can do in order to make that happen is you can make the cost associated with shipping to Miami less, meaning that, for example, right now, if you look at Detroit, which is the plant that is having less units supply, if you look at the cost, it is more expensive to ship to Miami than when compared to Denver. So if I want to make sure that I don't get short, maybe I can make this cost less, and let's see what happens. So as you can see now, just by reducing the cost, now Miami is getting all the units that were needed. So 1,400, and Denver is now the one that is getting short in terms of the units that were not supplied. So that's how can you make sure that you get the units? You have to look at the costs associated with shipping to the different destinations, and you need to make sure that your cost is less. And we can do the same thing here. Like let's put this back. I mean, we can choose one of the suppliers. So as right now, the other supplier is Los Angeles, because New Orleans right now is shipping all their units to Miami. So the other supplier is Los Angeles. So if I want Los Angeles to send units to Miami, again, I have to make this competitive, right? So one thing that I can do is to make this small, right? So if I solve this again, you are now shipping from Los Angeles to Miami because it's cheaper. So again, Denver is the one getting penalized. Let me put this back to the numbers, so 215. The other thing is you can penalize Miami, right? So if you make this, let's say 500 without changing the cost, if you use a penalty, you want to make sure that you get the units, right? So you're making this $500 if you don't deliver, then obviously when compared to zero, you don't want that to happen. So you are going to send that to Miami and not to Denver. I think if we make this $1, it's not gonna work. You have to make it big enough that when compared to the cost here, let's say, for example, if I make this one-on-one, yes. So since this is more expensive than this, then the model is going to say, okay, it's going to cost me more to not deliver to this guy, so I'm going to deliver him because I don't want to pay the penalty cost. Okay, so I'm going to make this Excel spreadsheet available in case you want to try different combinations. So let's go back to the lecture. We have the assignment model. Is a special case of the transportation problem. The classical assignment model deals with matching workers with different skills to jobs. Assumes skill variation affects the cost of completing a job. So the goal is to determine the minimum cost assignment of workers to jobs. So here's a description. So the idea is that you have these n jobs, which are represented here at the top. You have n workers, and you want to match a 1-1 match with the jobs and the workers. And there's a cost associated with assignment workers to jobs. The general assignment model has n workers and n jobs. The element Cij represents the cost of assigning worker I to job J. The assignment model is a special case of the transportation models. Workers represent sources and jobs represent destinations. The supply demand amount at each source or destination exactly equals 1. The cost of transporting worker to job is Cij. So this is the major difference between the transportation and the assignment, is that the demand for at each source destination always equals 1. The assignment model can be solved directly as a regular LP. Okay, so the agenda for this lecture was the definition of the transportation model, and then we discussed what is an unbalanced and a balanced transportation problem. And then we discussed the assignment model, which is a special case of the transportation model, with the difference that instead of having the right-hand side of the equations is always equals to 1, instead of having a larger number, if you want to say that way. So in one, you're assigning suppliers to demand nodes. In the other one, you are assigning workers to jobs. So a 1-1 relationship. So that's all for this lecture. And we'll continue with a different topic on the next video.